Hello everyone, my name is Yuhan Lin. Today I'm going to present our paper CDL. CDL is a classified distributed learning framework for detecting security attacks in containerized applications. Before we get started, let me tell you how vulnerable containers are. Here are some recent news I found online. And because containers are so vulnerable, we would like to detect attacks to containers. Containers are often short-lived, so it's difficult to get enough training data. Containers are often highly dynamic, so it's difficult to track normal patterns. Thus, existing solutions suffer from high false positive rate. False positives are costly to handle and may cause system administrators to ignore future alarms. We would like to solve those problems using our approach. CDL integrates application classification and online anomaly detection, which provides application-specific attack detection to containers. CDL is able to achieve high detection rate and low false positive rate. In this paper, we evaluate our system using Docker containers. First, we extract system call data from those containers and feed those data into application classifier. This classifier is able to tell what application it belongs to. After that, we have the classified system call data. Then we'll feed those data into system call data grouping. This module is able to group system call data based on the belonging application. For example, we can group the data from Elasticsearch together to train a neural network for later detection. And similarly, we can have another neural network trained using the data from Apache Tomcat and another model for Nginx. We can repeat the same process to train other neural networks for other applications. Once we have those models fully trained, we can use them for detection. For example, we extract the system call data from a Docker container and we will feed them into application classifier. At this time, application classifier tells that it is running Apache Tomcat, so we will use the model for Apache Tomcat to detect anomalies in this container. Similarly, we have another container and application classifier tells that it belongs to Elasticsearch. So we will use the model for Elasticsearch to detect anomalies. And that is the same for another container running Nginx. Now let's take a look at the system call overview together. CDL takes the input of system calls from Docker containers, and it will raise alarms if anomalies are found. CDL consists of 4 components. The first component is system call feature extractions, which extracts frequency vectors from the system call data. After having those frequency vectors, we will feed those vectors into application classification module, which can tell what application it belongs to. After getting the classified vectors, we will feed them into system call data grouping module, which groups system call data based on what application it is. After that, we have the group vectors, which is then fed into the final module of classified learning or detection. Let's examine each module one by one. For the first module, system call feature extractions, you can see that on the left there's a snippet of 100 milliseconds of system call trace. For every 100 milliseconds system call frequency is going to be extracted into one line of the table on the right. And you can see that the first red line indicates when attack starts, and CDL is able to raise alarm at few lines later. In the next line, we can see the new occurrences of LSIG and Z, and later on we can see the increasing trend of system call frequency across all system calls. The last line indicates when the attack ends. For the next two modules, application classification and system call data grouping, CTL implements application classification by random forest. Random forest consists of many decision trees, and each decision tree is able to make its own decisions. For example, in the graph here, it shows that how the random forest is able to classify that input vector. You can see that two of the three decision trees classify it to be Tomcat, and because of the majority voting, random forest will classify this input vector as Tomcat. Then we're going to append the classified frequency vector to the file corresponding to that classified application. For example, we can move this vector to the file belonging to Apache Tomcat, and we'll repeat the same process until we have gathered enough system call data for each application. Next, we use autoencoder as our main model for training and detection. Autoencoder will try to reproduce the input at the output layers as much as it can. And we will keep monitoring the reconstruction error during detection. Reconstruction error is the root mean square error between input and output. However, when autoencoder is fed with some data it did not see during training, we can observe high reconstruction error, and when the reconstruction error exceeds the threshold, we believe that an anomaly occurs. For our experiment, we collect 4 containers for each vulnerability we have studied, with different intensity of workload. We use Apache JMeter to deliver different workload to the containers, and we use Sysdig to collect system call data from those containers. We studied 33 real-world vulnerabilities from 24 server applications. As you can see from the pie chart, the majority of the vulnerabilities is retain shell and execute code. On the right, you can see that we mainly focus on vulnerability from the last 6 years, and all vulnerabilities has at least median severity score. For the evaluation methodology, we use true positive rate, false positive rate, and lead time. Lead time defines how early the attack can be detected before it succeeds. We then compare CTL with 2 alternative approaches, the sampling method and the monolithic method. The sampling method is that we train a separate model for each application using a sample of training data belonging to that application. The monolithic method is that we train a single model using all the training we have at a time. Recall that CTL uses random forest to implement application classifiers. Here we compare CTL's choice with 2 other application classifiers using SVN and extremely randomized trees. We can see that CTL achieved the highest true positive rate and the lowest false positive rate. Our explanation for this is that random forest is an aggregated model which is robust against noises. Now we compare CTL with 2 alternative approaches, the sampling method and the monolithic method. We can see that the sampling method achieved the highest true positive rate, however, its false positive rate is also the highest. That is because the sampling method underfits the data. We can also see the monolithic method achieve the lowest false positive rate at the cost of lowest true positive rate. That is because the monolithic method overfits the data. CTL achieve a good balance between true positive rate and false positive rate. We can see that CTL is able to achieve the near highest true positive rate and order of magnitude lower false positive rate. Here we compare the lead times of CTL and 2 alternative approaches, we can see that CDL is able to achieve a good lead time, especially for the largest thread in that category, written a shell and execute arbitrary code. CDL is able to achieve a lead time of more than 16 seconds. When comparing our paper with paper related to federated learning, CDL incorporates application classification to provide more precise detection models. And when comparing our paper with paper using distributed machine learning, CDL focuses on improving detection accuracy using data from similar applications to provide application-specific models with low training cost. To summarize, CDL is a new classified distributed learning framework which integrates online application classification and application-specific anomaly detection. We evaluated over 33 real-world attacks. CDL is able to reduce false positive rate by 98% and increase true positive rate by 66%. CDL supports real-time secure attack detection, which make it possible to be used in production environment. And finally, I would like to thank our reviewers and our sponsors. Thank you all so much for listening to my presentation. I'm ready to answer any questions you have.